So Johannes Müller is RPTU Karlsruhe Landau University, where he is a PhD candidate. The title of his talk is VeriCHERI, Exhaustive Formal Security Verification of CHERI at the RTL level. As I said, we were at the barbecue last night, so we had a very interesting conversation about this. And also, there were some armed people there as well. So, very fruitful conversation. Johannes Müller received his diploma in the degree in engineering and computing from engineering at the University of Karlsruhe in 2018, which I found out last night in southwest Germany, close to an hour from Frankfurt, if you want to locate it. He's currently a PhD candidate and researcher in the Electronic Design Automation Group at the same university, where he researches in the field of formal security verification. Okay, definitely not in conflict with Simon.
Thank you very much for the introduction. Yeah, so this talks about VeriCHERI, our security verification work on CHERI. So memory protection mechanisms are a key ingredient for security of the entire system stack. And one promising candidate is capability hardware enhanced RISC instructions, or short CHERI. CHERI is gaining a lot of traction in the industry lately. So ARM taped out the Morello processor. Microsoft actively developed CHERI at IBEX, an IoT-focused processor. CodaZip includes CHERI in their RISC-V processor lineup. And in general, there are RISC-V open source design available that implement CHERI. And as security mechanisms go in hardware, CHERI is quite sophisticated. So if we want to create trust for the entire system stack, we need security verification. There are related verification approaches proposed. So CHERI is intended as an ISA extension, and it comes with a formal ISA model, and there has been security verification on this ISA model. And in other works, it has been shown that this ISA model is compliant with or that the hardware implementation at the RTL is compliant with this ISA model. But the problem is that if you do security verification on a time abstract ISA model, you miss non-functional security vulnerabilities like timing side channels. And what we are attempting here is something completely different. So we do not start from a formal ISA model, but we start from global security objectives, in our case, confidentiality and integrity, and prove them or refine them to properties to prove them directly on the timing accurate RTL implementation. But before I talk about how we accomplish this, I want to quickly introduce CHERI. So CHERI enhances RISC ISAs with fine-grained memory protection implemented at the hardware. And CHERI is about capabilities. So capabilities extend classical address pointers, which are usually plain integers or integer addresses, with additional information like address bounds, access permissions, and so on. That means security memory accesses are done not with addresses, but with capabilities. And in order for memory access to be legal, it requires a valid capability that has the correct access permissions and is in bounds and so on. Right, I will skip a few slides in the interest of time. Okay, so in our work, we assume a capability enhanced single core processor with the memory for instruction and data. And the processor executes mutually distrusting tasks, and among those tasks is an attacker task. We also assume a trusted entity like an operating system or a hypervisor to securely manage the context switches between the different tasks. And for our formal verification, we model the hardware as a finite state machine. And most notable is that we model the finite state machine states as state variables, and those are all state holding RTL signals. And we denote the set of all state variables by set. And we decompose the set again into P, which contains all state variables belonging to the processor, and into M with all the state variables belonging to the memory. So we also model the memory as state variables in our model. Okay, now we take the perspective of a specific task. And for any specific task running on the processor, we can again divide M into MPUB, which includes all state variables pointing to memory locations that are accessible to the current tasks, and mprot, which contains all state variables which are not accessible, which are protected from the current task. And this compartmentalization of M into mpub and mprot is enforced by CHERI capabilities. That means if a memory location is in mpub, the current task has a capability that allows the access to this memory location. And if it's in mprot, the current task does not have access to such a capability. And an important thing to note here is that in our model, this is the only differentiator between two tasks, this compartmentalization into mpub and mprot. Okay, to reiterate our goal, so we want to prove global security objectives like confidentiality and integrity on the timing accurate RTL implementation. And we model our properties using non-interference. It's a strong formulation of security, and it's well known, widely adapted in security verification. So what is non-interference? I will explain it in terms of confidentiality and for our model. So in non-interference, you divide your design into high security locations and low security locations. And then you have to prove that information from the high security locations cannot influence the low security locations, or in other words, they cannot interfere with the low security locations. And we formulate this as a two safety model. So we introduce a second instance of the design, and we then assume that the low security locations are the same between the two designs. So the state variables hold the same value. We only allow a difference in the high security locations. And this difference is actually how we model the confidential data. And then we prove that from this point on, the low security locations remain the same between the two designs. That means the difference between the two designs and high security locations is not able to propagate to the attacker-controlled low security locations. This slide shows how we formulate this as a CTL property. It's basically the same thing that I just explained. So we assume that the public memory locations in the processor, the low security locations, are the same, and we prove that they remain the same. And we can do basically the reverse for integrity. So we now assume that the protected memory locations are the same and that they remain the same. So the attacker-controlled processor and public memory locations cannot influence the protected memory locations. But for proving those two CTL properties, two main challenges remain. So the first challenge is, how do we model mpub and mprot in terms of CHERI capabilities? And the second one is, we don't just want to model this compartmentalization of mpub and mprot for one task, but for any possible task that can be executed on the processor. And we have two key ideas that we use to overcome those challenges. And the first idea is that we model mpub and mprot not as state variables or not as RTL signals, but we model them by addresses. And then we can observe that the violation of the CTL properties is only possible if there's a memory access to the protected memory. And for confidentiality, that's a read access. So you first have to read the protected data in order to violate confidentiality. And for integrity, it's a write access. So this was the first idea. The second idea is a little more technical, and it starts with introducing a new symbolic address that can be chosen freely by the solver. And we also introduced a new macro, which we call CHERI protected, which constrains all capabilities in the system that an attacker has access to be fully symbolic. So they can have any value. They can protect or not protect any memory location, except they have to deny the access to the symbolic address. So the symbolic address is protected, the rest is either protected or unprotected. And then, since this symbolic address is also can be chosen freely by the solver, we model by this all possible divisions of mpub and mprot, and by this also all possible attacker tasks that can run in the system. We combine those two ideas into a new property for confidentiality, which essentially assumes that the symbolic address is protected and then checks if there can be read access to the symbolic address. And there are two notable things about this property. The first one is it's a one safety property. So it's a normal safety property. So we don't need two instances. That makes sense because you only need one instance to check if there's access to a specific address. And the second thing is that, can I have a pointer? Yeah, that the second AG here in this property is gone. So what we're formulating now is behavior that is that can be expressed in a finite time window. And this allows us to formulate an interval property. In this case, a property that only spans one clock cycle. And interval properties can be checked with SAT-based techniques and are quite scalable. So we do this basically the same for integrity, but instead of checking for read memory access, we check for write memory access. Okay, now we have two properties for confidentiality and integrity. But the problem is that we're assuming this CHERI protected macro. So the proofs are only valid for states where the CHERI protected macro is valid. And for global proof validity, we have to prove that this CHERI protected macro is actually an invariant of our current task. And we proved this by induction. Here on the slide, you can see the induction step that we're using. And there is an important there's an interesting connection to this to a concept that's fundamental to CHERI, which is called capability monotonicity, and it basically means that access permissions that capability can give you can only ever decrease. It's not possible to create a CHERI capability from another capability that has suddenly more access rights, and that's essentially what we're proving also here. So if the symbolic address is protected at some point, it will remain protected. There's no way that we can create a new capability that suddenly has access to the symbolic address. That's also why we call this property monotonicity property. Okay, now we have three scalable properties, and the question is, are we done? Do we have everything we need to prove our goals? And I will answer this with another question. What if the confidentiality one safety property fails? So what if it's possible to read protected data into the processor? Is confidentiality already violated? And the answer is, of course, no, because not all state variables in the processor are actually attacker visible. It could be that an exception is late and the exception will squash the data before it goes anywhere important, and then confidentiality is not violated. And we accommodate for this by introducing a new subset of P, which we call PARC, that stands for architectural or and contains all state visible all state variable, all attacker visible state variables. And we use this concept, let me skip this slide. We use this concept to introduce a less conservative property for confidentiality. And it's basically the same as the previous property, the two safety one, but we are now checking that the architecture state variables or the attacker visible state variables cannot be, or that the difference between the two designs cannot propagate or influence the architecture state variables. And that's really similar to our previous work on UPEG. I'm not sure if you're familiar with it, but we had a lot of papers on it. I will point out the main difference to our previous work, and that's this CHERI protected macro, that we take this perspective of a specific task. And with this, we can cover all breakout transient execution attacks. So a breakout transient execution attack example would be a meltdown attack. Okay, what if the one safety integrity property fails? So what if it's possible to actually to write to protect memory? There we say, okay, then the game is over, then integrity is violated, so the one safety property is sufficiently precise. Okay, so we have four properties, and we combine those properties in a verification flow, which we call VeriCHERI. I won't go into the details, it's just a specific order to structurally check those properties. I rather want to talk about our experimental results. And we conducted a case study on the CHERI at IBEX processor. So CHERI at IBEX implements a variant of CHERI that is tailored to IoT and real-time applications. And here on the slide, you can see a block diagram. This is an overview of our experiments in this table. So we started with the one safety integrity property, and we detected two functional bugs. And after they were fixed, the property held. Then in our VeriCHERI flow, we included a structural mechanism of detecting all registers in the system that contain capabilities and also all pipeline buffers that contain capabilities. We need this for refining our macro that we define. And we did this with the monotonicity property. And after several iterations, we are done with this. We used the one safety confidentiality property to check if there's a confidentiality violation. And here we split the proof again into data and instruction because there's a separate data and instruction memory interface. And for the data memory interface, we could show that it's not possible to actually read protected data. And for the instruction memory interface, we got a counterexample that showed that instruction fetches from outside the PCC bounds were possible. So the PCC is the program counter capability. It basically governs where it's possible to fetch from and where not. And so there's a suspicious case. We don't know yet if it's a security violation or not. So we have to investigate with our CHERI property. And indeed, we found that there is a side channel that can be potentially exploited in a transient execution attack. And it basically goes like this. So an attacker branches to an address from outside of the PCC bounds. That's an illegal instruction fetch, and an exception is raised. And then depending on two specific bits of this fetch instruction, the exception timing was delayed. So by measuring the overall performance, the overall execution time of the program running, or by observing the performance counter, you could probe for those 2 bits in an arbitrary protected address. All right, to conclude my talk, so CHERI detected several security issues, including vulnerability to a transient execution attack, and that's one case that's not detectable by previous methods. Much of our scalability comes from refining global security objectives to single cycle interval properties. And for our proofs, we required invariants that we developed, and we think that they would be quite similar on a similar project. So we published them open source. All right, thanks for your attention. Oh.
Thank you. Thank you. Are there any questions in the room for Johannes? Otherwise we'll go to, okay, let me run up there. Come to the end. Thank you. If you just want to come to the end. Yeah. Thanks. Should I introduce yourself?
Okay. Hello, I'm Katharina from ETH Zurich. Could you give some more details on how you came up with these invariants that you used?
Yeah, sure. So as I said in the talk, one invariant was this monotonicity property. It is basically not an invariant of the design, it's an invariant for the specific task. And there, it's basically, the challenge is how to refine this macro, how to really define that something is protected by a capability. And like I said, the challenge is here also to find all of the locations in the core where capabilities can be stored, and then with the symbolic idea that we symbolically model everything, we can cover basically this invariant. Another invariant that we needed is basically, we call it representability, because it's also called like this in the processor. And it's basically something you need when you have compressed instructions. So if there's not all bit combinations do actually express something meaningful, or they do not express a meaningful capability. And that's another invariant we needed. Then, of course, we needed, since we use in general a symbolic initial state for our proofs, we needed also design invariants that are part of the design. Yeah, that's something that would be not reusable, I think, just for verification on shared IBEX. I think we needed 5 invariants that we formulated by hand. It's not that much work, I would say.
Okay, that's a very good time to finish. So big thank you to Johannes, and we'll move to our next speaker. Thank you, Johannes.
Thanks.